Thank you. This is Yu from Tsinghua University. It is my pleasure to introduce EnFuzz, an ensemble fuzzing approach with seed synchronization among diverse fuzzers. As we know, fuzzing is, oh, sorry, I don't know what happened. Okay. Wait me for a moment. I think it is automatically, okay. Fuzzing is one of the most popular software vulnerability detection techniques. They have already found a large number of dangerous bugs and security vulnerabilities across a wide range of systems. There are mainly three types of fuzzers, and each type has its own fuzzing strategy. For example, generation-based fuzzer like EuFuzz and randomizer, they generate inputs by the specification of input format. The mutation-based fuzzers such as AFL and libfuzzer, they generate inputs by mutating the existing inputs. And the hybrid combining fuzzers such as Jitter and QSYM, they combine fuzzing with concurrent execution. Those fuzzers are usually evaluated with datasets such as CGC and LavaM with injected bugs. They are usually evaluated with metrics such as path number, branch number, and unit crashes or bug number. Based on these base fuzzers, there are different optimizations in different stages. For example, in the seed selection stage, AFL fast and AFL go, they will assign different priority to different seeds, like based on the frequency of the covered paths. In the seed mutation stage, FairFuzz, they use dedicated mutation algorithm to ensure that high-quality seed will not be destroyed. And also in the preparation stage, we usually will use a just sanitizer to harden the executed binary or use symbolic execution to generate high-quality seeds. But when we apply those fuzzers on some real-world applications, such as libssh and OpenSSL contained in Google fuzzing-test-suite, the strategies do not always perform well, and the effectiveness on different applications varies accordingly. From these four fingers, we can see that we chose AFL as the baseline and compare other tools with AFL on path coverage to demonstrate the issue of the generalization limitation. Here are the results. And from the picture, we can see that the performance of these fuzzers is challenged by the diversity of real applications. In almost half of the applications, the traditional AFL is the best. These problems also exist in the hybrid fuzzer of QSYM except for the generation and mutation-based fuzzer. And from the picture, we can see that if we do not use symbolic execution, the traditional results are good in maybe about 10 applications. But the symbolic execution only accelerates in 3 or 2 applications. In addition, we also ran those fuzzers in parallel mode, and here are the results. We can see that the generalization limitation did not only exist in single mode, but also in parallel mode. And in parallel mode, we find that the optimizations are not as good as the traditional AFL in parallel mode. The traditional AFL works better in most of the applications in the parallel mode. So how to improve the generalization ability? In machine learning domain, the ensemble learning is a good solution to this issue. What if we develop an ensemble fuzzing approach? Let's see a motivating example. Firstly, it takes 2 strings as the input, and the crashes when one of the 2 strings is magic string and the other is magic none. Suppose we have 2 different fuzzers. Fuzzer 1 good at solving the magic string problem, so it can cover T1 to T3 paths. Fuzzer 2 good at solving the magic none problem, so it can cover T2 to T6 paths. If we use them both and only ensemble the results in the end, we can cover 2 paths, 4 branches. However, if we ensemble these 2 fuzzers with some synchronization mechanism throughout the fuzzing process, once fuzzer 1 reaches T1 branch, it synchronizes the seed that can cover T1 to the fuzzer 2. Then with the synchronized seed, Fuzzer 2 can also reach T1, and because of the ability of solving magic number problem, Fuzzer 2 can also reach T4 fuzzer. Meanwhile, with the help of input synchronized by Fuzzer 2, Fuzzer 1 can also reach T2 and T5. Accordingly, all 4 paths and 6 branches can be covered through the ensemble approach. To achieve an efficient ensemble fuzzing, we need to deal with 2 main challenges. The first is base fuzzer selection. In this challenge, we should choose different fuzzers, expert in different domains. And the second challenge is the ensemble architecture design. In the second challenge, we should ensure that interesting seeds can be synchronized to all base fuzzers timely. Here is an overview of our ensemble architecture design. First, when a target application is prepared for fuzzing, we first chose several base fuzzers. The existing fuzzing strategies of any single fuzzer are usually designed with some preference, as the experiment before shows. In real practice, these preferences vary greatly across different applications. They can be helpful in some applications, but not effective in other applications. Therefore, choosing base fuzzers with more diversity leads to better ensemble performance. After the base fuzzer selection, we integrate fuzzers with the globally asynchronous and locally synchronous based seed synchronization mechanism. The key idea is to monitor the fuzzing status of each base fuzzer and share interesting things among them. Finally, we can collect crash and coverage information and feed this information into the final fuzzing report. For the base fuzzer selection, we class the diversity of base fuzzers according to 3 heuristics. The first is the seed mutation and selection strategy-based heuristic. For example, EuFuzz selects seeds that exercise low-frequency paths and mutate them more times. FairFuzz strives to ensure that the mutant seeds hit at the rawest branch. The second is the coverage information granularity-based heuristic. For example, libfuzz guides seed mutation by checking block coverage, while AFL checks edge coverage. The third is the input generation strategy-based heuristic. For example, Red Mesa and Peach use format specification, and others may learn the format during fuzzing to generate the seeds. Based on these 3 heuristics, we can select the different base fuzzers. We can choose the fuzzers as diverse as possible. The second step is the seed synchronization mechanism. The main idea is to identify the interesting seeds of each base fuzzer and share those interesting seeds synchronously among all fuzzing processes. It employs a global local style data structure. The local seed queue is maintained by each base fuzzer, while the global pool is maintained by the monitor for sharing interesting seeds among all base fuzzers. In ensemble fuzzing, the union of these base fuzzers result is needed to identify interesting seeds during the whole fuzzing process. Accordingly, the global coverage map is designed, and any new paths or new branches covered by the interesting seeds will be added into this global map. This global map can not only help decide which seeds should be synchronized, but also help to duplicate and share the results. In this step, we will collect the interesting seeds of each base fuzzer and then store in the global map and then dispatch these seeds to each basic fuzzer. For the implementation, we first chose 6 popular fuzzers as base fuzzers based on 3 heuristics. We chose AFL, AFL-fuzz, FairFuzz, and libfuzz. They are mutation-based fuzzers. And we also chose Red Mesa, they are generation-based fuzzer, and also QSYM, it is the hybrid fuzzer. During the implementation, we need to address the following 4 main engineer problems. The first is the standard interface encapsulating. Because different fuzzers, they use different standard or driver, interface driver, we need to use a standard one. The second challenge is the libfuzz continuously fuzzing. Because libfuzz, they will stop when a crash is found, and also the crash deduplicating and charging technique. Also, the seed synchronization, the result in the grading method is implemented. We implement 4 types of ensemble fuzzing based on different base fuzzers. EnFuzz A, it is based on mutation-based fuzzing only, AFL, AFL-fuzz, and FairFuzz. EnFuzz Q is based on AFL, AFL-fuzz, FairFuzz, and QSYM. EnFuzz L is based on AFL, AFL-fuzz, FairFuzz, and libfuzz, and EnFuzz is based on the 3 mutation-based fuzz and Red Mesa. We evaluate on two datasets. The first is the LavaM, and the second is Google Fuzz-test-suite. Each tool is run on, was run on ASIN head and binaries with 4 fuzzer instances for 24 hours. First, let's see the results on LavaM, which I think it is a small size of benchmarks because the code size is between 2,000 to 5,000 lines of codes. From these results, we can find that symbolic execution-based method outperforms mutation-based fuzzers. The result is amazing, I think, because symbolic execution is good at solving the complex branches and find significantly more bugs. But when we integrate any symbolic execution into the original mutation-based fuzzers, the seed synchronization mechanism performs very well and will outperforms QSYM. For the results on the Google Fuzz-test-suite, we can find that EnFuzz outperforms all other fuzzers on each project. The first 6 clones of this table reveal the issue of the performance variation in those space fuzzers, as they perform variously on different applications. But compared with AFL, libfuzzer performs better on 15 applications, but worse on 9 applications. RedMesa performs better on 8 applications, but also worse on 16 applications. QSYM performs better on only 9 applications, but worse on 15 applications. For the EnFuzz, it is the best on both pass coverage and also the bug detection number. From this table, we can find that EnFuzz can discover 16 unique bugs, not unique crashes, because we also deduplicate the unique crash for unique bug and also manually confirm and identify each unique bug. From the result, we can find that EnFuzz it detects the most number of bugs. And also from this table, we can find that on different datasets, different fuzzers, they perform differently. On the LavaM dataset, QSYM is the best and find lots of bugs and lots of pass. But on the Fuzz-test-suite of Google, we found that traditional AFL finds more bugs than QSYM, and also the libfuzzer also found more bugs than QSYM. Without symbolic execution, the performance is even better. We also chose AFL as the baseline and compare Ensemble Fuzzers with AFL on pass coverage to demonstrate the performance of Ensemble Fuzzing. As mentioned before, we implement 4 types, and we want to demonstrate what will happen of these 4 types. We can find that more diversity of those space fuzzers in fuzz configuration will perform better. As we can see from the picture that Ensemble Q performs better than Ensemble A, Ensemble L performs better than EnFuzz Ensemble Q, while EnFuzz always performs the best. EnFuzz performed the best because we chose the different fuzzers. They belong to 3 different types, not the 2 types or 1 types. So the result is better. From this picture, we can see the overview of the Ensemble Fuzzing, the performance. MXML is a widely used XML library, read XML data and stream from the application. We can see the number of pass, branch, and unique crash and unique bug. From this picture and the statics, we can also find that maybe unique crash is not a good identification of fuzzing. Because from the picture and the number, we can see that the 17.7 unique crash only refers to 1 unique bug. And the second EnFuzz, it has 919 unique crash. It only has 4 unique bug. Maybe I think unique bug may be better than the unique crash. If we apply EnFuzz to more real-world applications, we can find that more real bugs has been detected. We apply EnFuzz to fuzz some more well-fuzzed projects, such as the image processing library libpng and libjpeg, the video processing library libwav. Those projects are well-fuzzed of existing work such by AFL, by AFL Faster, by AFL Go. But there are lots of vulnerabilities or bugs that has not been detected before. But with EnFuzz, we can get those bugs covered, and 6 more unknown bugs, including 44 successful registered CVE. For conclusion, I think the generalization limitation certainly exists in existing fuzzers and existing optimizations. Maybe ensemble fuzzing is a good solution. We should try to integrate different optimizations together to achieve a better performance. And the results also show that EnFuzz is very effective. But there are also some problems. For example, when we integrate AFL fast and FairFuzz together, we found that if we integrate them together, their performance will decrease because the optimizations of them are conflict. And we need to address those conflicts during our ensemble optimization. We also provide a website version for free trial of EnFuzz, and everyone can use the server for free fuzzing and testing. Yeah, thank you.
Hi, this is Mohammed from USENIX. Thanks for the great project. I have a question about the slide 22.
22.
Yeah, about the evaluations.
Yeah.
It shows that EnFuzz, for example, finds 60 bugs in total, but EnFuzz runs a couple of these fuzzers together.
Yeah.
And do we know that if we run the fuzzers that EnFuzz run independently, how many unique bugs they can find in total? Because, for example, AFL found 34 bugs here, and other one found 33.
Yeah.
They might not overlap completely.
Okay, this is a very good question. Yeah, because I think this is a missed experiment in the paper. Maybe we need to manually identify the bugs. Which is overlap, which is not overlap. We supplement it as a supplemental file in the GitHub. You can find that in the 16 bug, 26 that are not covered by those existing fuzzers. Yeah.
Nice. Thanks.
Hey, Zafir from UC Irvine. Really nice talk. I was wondering, do you have a plan to bring this to kernel fuzzing? And if you have a plan, what will be the heuristic?
I think to kernel fuzz, I think it is hard work, I think. Because the metrics used in kernel and application, I think it is different, and we cannot easily customize our selection heuristic to kernel fuzz, I think. Yeah.
Nice. Thanks.
Let's thank the speaker again.
Yeah.